Konstantin Tsiolkovsky was a very famous Russian visionary of space travel. He was a school teacher out in rural Russia and received essentially no government support until very late in his life when his work started to be recognized. But on his own, he essentially not only derived the rocket equation, but speculated on many aspects of space travel, what it would be like being weightless, how you could build a space station with artificial gravity, problems of radiation in space, all sorts of things. So Tsiolkovsky, really an amazing guy. And let's now take a look at what his famous rocket equation actually means for rocket science. So here's the rocket equation that we just derived, and we can change it from the logarithmic form to an exponential form, and we see that the ratio of the initial to the final mass, that is before and after you burn the propellant, is the exponential of the change in velocity, which you get from burning this propellant, divided by the exhaust velocity. Now we'll see why a statement that I made earlier is actually true. I said that the critical things in the performance of a rocket engine are, first of all, how much material you can throw out the back, and that is the more your initial mass can be compared to your final mass, because that's all the propellant, and how fast you can throw it out the back, and that's the exhaust velocity. Now let's take a look at what that means. We can look at, for instance, the mass that is the propellant, which is just the initial minus the final masses, and just a little algebra, and we can get expressions for that. This is important because it's often referred to as the propellant fraction. That is, when you start out with the rocket fueled up on the launch pad, what fraction of its total mass has to be propellant in order to get you the velocity that you need. So that's how we would derive it. And the rest of it is inert. You can actually do lots of algebra on all of this. But let's look at why the exhaust velocity is so absolutely critical. For typical chemical rockets, that is all the way from solid rockets, which are at the low end of the scale, their exhaust goes out at about 2 kilometers a second. The most efficient liquid propellant rockets burning hydrogen and oxygen, they can push their propellant out at about 4.5 kilometers a second. And by the way, just in case you ever run across the expression specific impulse, engineers use this for various historical reasons, which I won't go into, but there's a very simple relationship. The exhaust velocity is the specific impulse multiplied by the acceleration of gravity at the Earth. That is 9.8 meters per second squared. And it doesn't matter if you're taking off from Mars or the Moon or Jupiter or wherever, you still use G0, the acceleration at the Earth's gravity. So chemical rockets have specific impulses roughly from 200 to 450 seconds, and that's because its acceleration here and velocity, the specific impulse, is in seconds. Okay, so what does this all matter? And why do we care about having a higher or a lower exhaust velocity? Well, orbital velocity in low Earth orbit is about 8 kilometers a second, but if you're launching through the atmosphere, you have atmospheric drag and what we call gravity losses, which I'm not going to go into now. We'll talk about flying through the atmosphere a little later. We're also not going to talk about the fact that the Earth is spinning. Let's just assume that we need to have a velocity change of 9 kilometers per second to get to orbit. Now, let's put in some numbers. Suppose we're using a solid rocket with a typical exhaust velocity of 2 kilometers a second. So the delta V of 9 divided by the exhaust velocity of 2 gives us 4.5. And when we put that into the rocket equation, we see that the ratio of the final to the initial masses is just a little over 1%. What does that actually mean? It means that the mass of the propellant when you're sitting on the launch pad has to be 99% of the entire mass. That means that only 1% of the mass can be devoted to the structure of the rocket itself and the payload that's sitting up on the top. And that's not enough. Frankly, we can't build a rocket like that. But now let's look what happens if we just double the exhaust velocity, okay? Just a factor of 2. Now that ratio is 2.25, but the critical thing, and here's what you have to remember about the rocket equation, that critical number is in the exponential. We've only changed the exhaust velocity by a factor of 2, but look what it did to the ratio of the propellant to the initial mass. We now can devote up to about 10% of the mass of our rocket to the structure and the payload because our propellant fraction is only 89%. So instead of 1%, we've gone all the way up to 10% of mass that we can devote to the structure and the payload, even though we only changed the exhaust velocity by a factor of 2. And that's the real essence of the rocket equation. You're dealing with this exponential, and increasing the exhaust velocity by just a little bit can really make a huge difference in the performance you get out of the engine for a given amount of propellant.